Okay, hello everyone. When we go ahead and take a look at our first order differential equations, one of the first things that we're going to take a look at is to see whether or not we can separate the variables. So again, notice that if we can go ahead and say that d of y over d of x is equal to some function in terms of x divided by some function in terms of y, then what I can do is I can separate the variables and integrate both sides to come up with the solution to the differential equation. So notice that, like say for example, if I have this equation d of y over d of x is equal to xy plus y divided by x squared plus 2x. If I go ahead and factor out the y, then I can go ahead and divide both sides by y and multiply both sides by the differential dx. And what I come out with is something that looks like this. The 1 over y d of y is equal to x plus 1 over x squared plus 2x d of x. Now, what comes into play now are all of our integration techniques that we worked with before. What I'm going to use is a u substitution here. Let u be equal to x squared plus 2x. Because if I take the derivative of both sides with respect to x, I come out with 2x plus 2. And if I factor out the 2, I come out with x plus 1 d of x and 1/2 d of u on this side. And then I can go ahead and substitute to come out with a much simpler integral of 1/2 integral of 1 over u d of u. Now, of course, this one over here is going to be very simple. I can just go ahead and integrate that to say that that's the natural log of the absolute value of y. This right-hand side then simplifies to 1/2 natural log of the absolute value of u plus c. And then I just need to go ahead and resubstitute x squared plus 2x for u. Now, how do I go ahead and solve for y? Because remember, that's what we're trying to determine. We're trying to determine what the solution is, and we want to have that as y equals something. So, come up here. Now notice that if I wanted to go ahead and change this a little bit, I'm going to go ahead and rewrite this using our rules of logarithms and just say that this is a natural log of the square root of x squared plus 2x. And then I take the exponent, change it into its exponential form. So I have the absolute value of y is equal to e to that there. And then I use my rule of powers, okay, my index laws, and I come out with e to the c times it by e to the natural log of the square root of x squared plus 2x. Now e to the c is just going to be a constant, so I'm just going to go ahead and call that c again, and then this is just going to be the square root of x squared plus 2x. Now this is actually going to be equal to the absolute value of y, so if I want to solve for y, that means I'm going to have with plus or minus c times it by the square root of x squared plus 2x. But again, c, we know that that's going to be just a constant, so I can just absorb that and just call it c. Square root of x squared plus 2x is going to be equal to y. So when we go ahead and deal with this first particular example here, we can actually separate the differential equations. By separating them, we can then go ahead and integrate both sides, and we can come up with a solution. Okay? Okay, the second method that we're going to take a look at in order to solve first order differential equations is looking at something called a homogeneous differential equation. Now, what we're going to see is that if we can come up with a first order differential equation that can take this form here, where we're going to have to look for this y over x, then these type of first order differential equations are known as homogeneous differential equations. Now, in order to solve these, what we're going to do is we're going to let y be equal to v times x, where v is a function in terms of x. Okay, and by using this substitution, you'll be able to separate the variables x and v, and then solve accordingly by integrating both sides. Now, let's take a look at an example here. It says d of y over d of x is equal to x plus 2y over x. Now, notice in this case, there's no way that we can actually separate the variables at this point. But what we should notice is that we can actually rewrite this particular right-hand side of the equation to 1 plus 2 times by y over x. So notice there's the function y over x that we're looking for. Now, again, once we see that particular factor here, what we're going to do is we're going to let y be equal to v times x. And if that's the case, then we know that d of y over d of x from here is using, and then if we go ahead and differentiate both sides of this with respect to x. I have to now go ahead and use the product rule. This is going to be v times it by the derivative of x, which is just 1, plus x times it by the derivative of v with respect to x. Okay, and so that's what we come up with there. In addition to that, we also know that v is going to be equal to y over x. Okay, now look at what happens. Once we go ahead and find this form, which is the homogeneous differential equation, then I can go ahead and rewrite d of y over d of x as v plus x d of v over d of x, which is right here, which is going to be equal to 1 plus 2 times it by v, because the y over x again was going to be v. Now notice what happens is that I can go ahead then and subtract v from both sides, and now what I have is I have a separable differential equation. So I go ahead and separate them, integrate, come out with the natural logs here. Now notice I need to go ahead and resubstitute y over x for v, because again what we're trying to do is we're trying to solve for y. And then I can go ahead and take the exponential of both sides to come out with e to the natural log of the absolute value of x plus c is equal to c times it by the absolute, which is going to be equal to c times the absolute value of x. And then what I have then is y over x is going to be equal to c times the absolute value of x minus 1. Solve for y by multiplying x to both sides of that equation. Okay, and there you go. That's how we can go ahead and solve for a homogeneous differential equation by noticing that we can rearrange the particular values here to include y over x's. Okay, so we'll take a look at one more method. Okay, let's look at our last means of solving for first order differential equations. Now this integrating factor method is a little bit complicated because it's going to take a look at a particular first order differential equation that takes the form of d of y over d of x plus y times it by a function in terms of x called p of x equaling another function in terms of x called q of x. So the main thing to look at is that this right over here is your d of y over d of x. You got plus y times it by a function in terms of x is equaling another function in terms of x. Now notice again, we're not going to be able to initially separate those two. So what we're going to have to do is we're going to have to actually create a function called I of x. And this is what they're going to be considering to be called the integrating factor. So I of x, and what I'm going to do is I'm going to actually multiply the integrating factor function to this part right here, which is our given initial form of the first order differential equation. So notice I just have I of x associated with each one of these parts here. Now the next thing that I'm going to do is I'm going to assume that the derivative of I of x, the integrating factor times it by y with respect to x, is actually going to be equal to this left-hand side here. Okay, I'm going to assume that that's true. Now what I'm going to do here is notice that this part right here just follows. Okay, that's exactly the same thing. Now what I'm going to do is I'm going to go ahead and I am going to use the product rule to find out what the derivative of this actually is. So I'm going to come out with I of x times it by d of y over d of x plus I prime of x times it by y. Now I'm assuming that these two are true. Okay. So what I can notice then is that these two are actually going to cancel out because they're the same on both sides. So I'm left with I prime of x y is equal to I of x y p of x. Now notice the y's will cancel out and I'm just left with I prime of x is equal to I of x times it by p of x. Now what that means then is that if I actually go ahead and solve for p of x is just going to be equal to I prime of x divided by I of x. Now if I integrate both sides with respect to x, I'm going to come out with the integral of p of x d of x is equal to the I prime of x divided by I of x d of x. Now if you think about that, wow, that's exactly the same thing as using a substitution rule and coming out with 1 over u. So what I'm coming out with then is that this is going to be the integral of p of x d of x, and that's just going to be the natural log of I of x plus c. Subtract c from both sides. Solve for I of x by changing it to its exponential form, and I come up with something that looks like this: e to the negative c plus the integral of p of x d of x. Now, of course, this is going to be e to the negative c times it by e to the integral of p of x d of x. And so what I'm going to do is I'm just going to call this value a. And that's going to be my parameter a, my constant there. So this is what my I of x actually is now. Now, how is that actually going to be helping me solve the differential equation? Now, we need to go back to this step over here. When we actually took a look at this, I assumed that this was true. And I went ahead and I just looked at this part, and I assumed that this part was equal to that part. But I also know that this right over here in my assumption, that this is also going to be equal to this, because I already said that this, which is equal to this, which is the same as that, is also equal to that. So what I have then is I have the derivative of I of x times it by y with respect to x is going to be equal to I of x q of x. Now what that means then is that if I integrate both sides with respect to x, I just come up with ixy is equal to the integral of ix q of x d of x, and therefore I can now solve for y, and wow, I've solved for y. So what happens then is that if we actually go ahead and note that we can come out with a first order differential equation in this form here, I know immediately that I can use my integrating factor here, and once I know what my integrating factor is, I can go ahead and solve for y by using that there. So let's go ahead and take a look at an example. For example, if I have d of y over d of x plus 3y over x is equal to 8x to the fourth, and let's say that I'm given that the solution, whatever it is going to go through 1, 0. Now, take a look. That's exactly this form here. I got the d of y over d of x, I got the y, p of x, of course, in this case is going to be 3 over x, and the q of x is, of course, going to be equal to 8x to the fourth. Now, once I know that I got this, and I know what the parts are, I can then go ahead and say that I of x, or my integrating factor, is just going to be a times it by e to the integral of p of x d of x, and in this case, p of x is just 3 over x. So what I come out with then is a e to the 3 natural log of x. This is a e to the natural log of x to the third. So that's just going to be a x to the third. Excuse me. So once I know what my integrating factor is, now I can go ahead and substitute everything in here to solve for what y is. So I know that y is going to be equal to 1 over my integrating factor, which is of course ax to the third. And then I'm going to integrate ix, which is ax to the third, times it by q of x, which is 8x to the fourth d of x. So notice that what's going to happen is that the a's are going to cancel, and the 8 can be put outside as a scalar. And then I have 8 over x to the third times by the integral of x to the 7th d of x. Now, what happens then is that I come up with 1 over 8 x to the 8th plus c, and that is going to be multiplied to this part here. Now, I need to go ahead then and distribute, and what I come out with is x to the 8th plus c divided by x to the third. Now, you might be asking, okay, where did the 8 go when I distributed this to that particular c value? Well, 8 times c is just going to be the same thing as c, which is a constant. Now, this is going to be what my general solution will look like. Now, I know from the given problem here that the particular solution that we're looking for is at going through 1, 0. So if I substitute 1, 0 for x and y, then I know that c is going to be equal to -1, and I can come up with a particular solution, which is y is equal to x to the 8th minus 1 divided by x to the third. Okay, so this is the integrating factor method. Again, it's important that you realize that we can get the first order differential equation into this form here. Once we see it in that form, we can use our integrating factor once we identify what p of x is. And once we identify what p of x is and q of x is, we can then go ahead and use those to come up with our integrating factor to then go ahead and solve for the differential equation. So there you go. We'll go ahead and take a look at some of the equations that have this form the next time that we have class. So see you then, and we'll take some questions during that time. Bye-bye.